All right, let's look at this one. We have a colony of fruit flies that grows at a rate proportional to its size. And initially, there's 20 fruit flies that are present. And then in 5 days, there's 400. What we want to do is determine a function that expresses the size of the colony here as a function of time, where we're measuring time in days. So what this is really saying is find the population function. So that's what we want to do. We want to find our population function P of t, where we're measuring t in days. All right, so we have to look at what information we're given. So we have this colony of fruit flies, and it's growing at a rate proportional to its size. So first thing, right away, when we see this phrasing, growing at a rate proportional to its size, that immediately says we have exponential growth. So that basically tells us what our function is. It's going to be our initial population and then e raised to the power k times t. Or that alternative form if we want to use that. We're going to use this form here for our calculations, but you could try it with that other form. So right away, we see this phrasing, grows at a rate proportional to its size. That immediately tells us what our solution, what our function is going to be. Now it's up to us to then figure out, there's two things we need to figure out in this equation. We need to figure out what our initial population is, P0, and then we also have to figure out our growth constant, constant K. So this is where the other information comes in. All right, so we want to determine P0. Sometimes we're given this, sometimes we're not. We have to figure it out. In this case, we're actually told, initially, 20 fruit flies are present. So that actually tells us what our initial population is. So that tells us our starting population at time 0 is 20. So let's update our function. Let's look at our updated function now. So we're going to replace that constant in front with 20. And then we'll have e raised to the power k times t. All right. So we still need to find k. So that's the next thing. We want to find our growth constant. We want to determine k. And we have to see what other information we're given. And we see that we're given this information that in 5 days, our population is up to 400. So that's telling us after 5 days, our population is equal to 400. All right, so let's actually plug this value for t into the function we have so far and see what we get. So our population after 5 days is going to be 20, e raised to the k, and then we're plugging in 5 for t. So there'll be a 5 up there. And we know this should be equal to 400. So we set it equal to 400. And this gives us an equation. If we look at those two pieces there, this gives us an equation then that we can solve for k. So we're going to solve that for k. So let's do this right down here. So we have 20 e to the 5 times k. I like to put the constant, we don't know what k is, so we're going to figure that out. I like to put the 5 in front. Doesn't really matter. This is going to be equal to 400. And so this is an exponential equation. And the way to kind of solve this is we want to isolate first we want to isolate the exponential piece. So let's divide both sides of this by 20. So when we do that, that'll give us e raised to the 5 times k. And actually, let's leave a little bit of space here. A little bit of space. And then when we write the other side of our equation, let's leave a little bit of space next to this equal sign. So 400 divided by 20 is 20. And so that's good. We've gotten rid of the constant in front. Now the next thing to get rid of is this exponential, the exponential function. We want to kind of undo this exponential function. And the way to do that is with natural log. So we're going to apply natural log to both sides. And why natural log? Well, it cancels nicely with our natural exponential function. They're inverse functions of each other, so they cancel out. That's why we had to get that 20 out of there. So the natural log and the e were kind of right next door to each other, and they would cancel. So what does this do? Well, this gives us 5k on the left, and that's equal to natural log 20 on the right. And then now natural log 20 is just a fancy looking constant. We want to know what k is, so just divide both sides of this by 5. And we get k is equal to natural log 20 over 5. And there we go. We've found our last piece of our function here. So now we can say our population function is 20 times e, and we know what k is. So it's natural log 20 over 5 times t. And t is our variable. So there's our nice population function. And we can answer all sorts of questions with that now. So if we wanted to know what the population would be after 10 days, plug 10 into that function. If we want to know the population after 8 days, just plug 8 into that function. So it's a handy function to have. It models the population, how many fruit flies we have in this particular colony after so many days. All right, so we're going to try another example with, what is the next one? More bacteria? More fruit flies. We'll try another fruit fly example. We'll see you there.